Now, each contour or each curve is a collection of points that have the same height value or elevation in this case, right? So this is a very useful visualization. It tells me where the mountains are, where the flat regions are. For example, I can see that these are the flat regions, and I see that there is probably a mountain top here, right? Another mountain top here, and so on. So it helps me understand the elevation and the gradient of the elevation over this map, right? So it's a very useful visualization. Unfortunately, this visualization does not scale well, especially when the data becomes rich in features. So let's take this example in 3D, right? Where I have, instead of a 2D example such as this, I have a 3D example where I collect the set of points that have a given real value for the function, and I extract that surface. So instead of curves in 2D, we have surfaces in 3D space. You can quickly see that this visualization becomes messy. It's very difficult to understand what are the features, right? Even when you can figure out what the features are, it becomes difficult to choose an appropriate surface. So in this example, we have a CT scan of the human feet. So this is a volume, and you can extract different surfaces from this. If for given different scalar values, so for a value of 30, you get kind of the skin structure together with a little bit of the ambient space. Here you have a scalar value of 80, and for that you get a nice skin surface, which is extracted as the what's called the level set. So for slightly higher values, let's say 200, so these are the set of points in the volume which have a scalar value of 200, and you can see that that corresponds to the bones, right? So this is a nice visualization, but even here there is a challenge, right? What if there are not just 2 interesting values, but there are 10 interesting values? I will not be able to show all these isosurfaces together, or I will not be able to show all these surfaces together, because one will occlude the other. You can imagine that the bone actually sits inside of the skin structure. I cannot see both at the same time. How do I identify which value, 80 or 200 or 150, right? Which one do I choose? So this is also difficult. So that's another challenge. One way to address this challenge is to produce what is called volume visualization, where I use transparency to be able to see through a volume. So here, for example, I'm able to see through this volume and show the bone structure, the blood vessel structure, and the skin structure all at the same time, right? So this seems to have to help us address this issue with occlusion. However, the data throws other challenges at us. The data can become really, really complicated that you may not even be able to see through. There are so many features. For example, in this, what is called the Millennium simulation. This is a simulation of the entire universe. What you see in these golden colors are the galaxies clusters. So these are clusters where all our galaxies sit. Now, in addition to these galaxies, there are these small thread-like structures that connect the galaxies. So these thread-like structures are also important. A few galaxies sit there also, but it's very difficult to extract them meaningfully. And visualizing them is even more a challenge. So this picture, while it is pretty and it shows to some extent what are the clusters, it is not useful for a cosmologist. It is not useful for somebody who is studying the universe, a physicist who is studying the universe. So we need better techniques to visualize such complex data. So more specifically, the data produces these challenges. The size of the data becomes large, and this causes a lot of trouble for us. The data becomes feature rich, as in there is a lot of interesting things in the data, and as a human, I'm not able to pay attention to all the features. So I would like my visualization to focus on the interesting parts, such as the data from the cosmology study. Time varying data is another challenge. The way we want to address this is by integrating this visual representation and some analysis. So I want to use some abstract ways of showing what the data contains. Let's use an example. So here, I'm not sure how to remove this. Can somebody help me here? So Vinod, will you be able to?
Yeah, I'm here.
Yeah, so there is this green streak. I just want to be able to remove that. Okay. I see an eraser. Okay, good. Okay, so let's move forward with that. Oh, there is one more streak now. Let's see. Okay. I don't know if this is what is causing this, but anyway, let's move forward. So I want to be able to right. So I was talking about the challenges in visualization, particularly when the data was represented as a scalar function, right? So now I want to quickly switch gears just to say that so the data need not be only of this form, right? So by the way, Professor Vinod, there is a lot of background for me from my end. I don't know if you are still able to hear me. Can you just confirm?
Yeah, we can hear you. No problem. There is no noise at all.
Okay, if you'll just give me a minute, I will switch to another room. Unfortunately, there is construction happening nearby. Just give me 1 minute, please.
Okay, okay.
Okay, I'm back. I hope you can continue to hear me. Right. So, right. So I was trying to motivate the need for visual abstractions to enhance visualization. So let's use this example, right? So the example here again is the CT of a human torso, right? So this CT, if you can, let's look at this. Right. So this is a CT scan of a human torso. So we can already see a few interesting structures here. This is the visualization here is called volume rendering. But I would like to enhance this visualization, and the way I will do that is by constructing this graph called the contour tree, right? And the contour tree captures interesting features within my data. So I am able to select individual arcs in the contour tree. For example, you see that two of the arcs here are selected. The pink ones are selected. I would like to use those arcs to highlight interesting parts of the data. And so this is what I get after I highlight the interesting part. So the visualization in the middle is directed by this, if you want to call it a user interface, that's also fine. This is a very sophisticated topology directed user interface. And selecting individual arcs here allows me to select, for example, the lung structure and the colon and the bone structure, while the gray are all the background, the skin and the vessels and so on. They all go into the background and as context. So this the visualization here at the center is much better at telling us what are the interesting features within my data. So this is what I would like to do. And the tree here is a visual abstraction, and it comes from the study of the topology of this scalar function. So that is the motivation for using topology for visualization, right? So now I want to switch gears a little bit and talk about another form of data, right? So this is data which comes from a tabular or columnar kind of data, right? So most common example these days is health data or the number of COVID-19 cases, right? So these come to us as a collection of records, right? So where every record has multiple attributes. So for example, in this case, the case of Bangladesh, you have multiple attributes like population, the number of physicians per 1,000 people, hospital beds, expenditure, and so on, right? And you have, this is one data point. Similarly, the other data points are the other countries. So this is a high dimensional data, a data that comes from dimension, which is probably, if there are like 10 rows here, it's 10 dimensional data. Now, one way to understand this data is by thinking of this as a point, each data as a point in 10-dimensional space, right? The way topology comes in here is, if you can understand the shape of the set of points in the high dimensional space, then you understand a little bit about patterns in your data. So for example, if these are the points in the high dimensional space, you can quickly see that there are 3 different clusters, right? So so you can say that there are 3 different collections or components in my data, right? And then we may want to drill down and understand what each component or each cluster represents, right? So this is something that many of you may already be familiar with, right? So it's clustering of high dimensional data. It's nothing new. But let me now talk about something that you may or may not have thought about, right? To the human eye, I can see that there are 3 different clusters here, right? But what if there is noise, right? I just introduced like 4 or 5 points, additional points, and these were noise points. Do I still see the clusters? If I actually did not show you the clear clusters on the left, you may or may not have noticed that there are 3 distinct clusters here on the right. So identifying clusters is not an easy problem, right? This is just to motivate that fact. Identifying components or clusters is not an easy problem, particularly when the data is noisy, right? Even if the data is not noisy, there may be no clear clusters in your data, right? So this is something that many of you who have done any data science or machine learning have seen. But let's take this forward a little bit. Remember, we are now talking about the shape of this data, right? So the shape, as in you have 3 clusters. Now the shape could also be in other forms. So here is a very interesting collection of points. I can quickly see that it forms one cluster, right? But it also exhibits a cycle or a loop or a hole, right? Different terms for the same thing. So this is an interesting pattern in the data. This is also contributes to the shape of this data, right? The same issue here. What if the data is noisy? I do not see the loop or the cycle as clearly as before, right? So the question is, how do I, the natural question is, how do I identify the number of clusters? How do I identify the loops or cycles in my data, even if there is noise in the data, right? So we don't stop there. Shape could be in other forms. For example, here is another form of in which we want to study shape. So we have a fork in my data, right? So there are clearly three different tentacles to the data, and the collection of data in each tentacle could represent something different, right? So for example, if you have your records come from, let's say, medical records, maybe this is a set of patients who have one type of diabetes, and here is a set of patients which have a different type of diabetes. Maybe this is a third normal collection of human beings, and there is a nice intersection between three of human beings who exhibit some form of these two diabetes, but you may also want to call them normal, right? So there are forks often in the data, right? So there are all these nice patterns, and topology helps understand these different shapes, right? Now, how does topology help us, right? So I already talked about clusters and loops and forks. So all these three notions are determined by how the set of points are connected. So for those of you who have already done topology, you know that that is essentially what we study in topology, right? We study how spaces are connected. But I introduced everything using pictures here. So I just showed you points, right? And to the human eye, we kind of interpolated and were able to figure out the different shapes, and we made some assumptions about the connectivity and so on, right? But if you want to do it on the computer, you need to explicitly say what space you are talking about. So here is a very simple example. Instead of talking about individual points, you talk about points and disks centered at those points, right? So the disks are shown in red now, and what you see is the union of all these disks, right? So this gives you a continuous space, and the notion of connectedness can be more easily defined here, right? And now you can talk about representing this shape, right? So this was just an intuitive introduction to an alternate form of data and how topology could help you understanding patterns or interesting features in this data, right? So with that kind of introduction, let's talk a little bit about topology. For those of you who may not know topology or who may not have seen it before. If you know, then think of this as my way of introducing topology for the rest of this talk, right? So the folklore definition of topology is what topologists do. And what do topologists do? So the topologist is somebody who drinks a lot of coffee, eats a lot of vadas or donuts. And topologist is one who does not distinguish between the two, right? For a topologist, the coffee cup and the donut is the same, right? So of course, this is there is some element of truth to it, but this is not fully true for all the topologists out there, right? So maybe a little bit more not formal, still informal. Topology is the study of connectivity of space, right? So we study different notions of connectivity, and the way we study connectivity is by defining invariants of space, right? So what is we'll start with a very, very simple invariant that comes more from graphs, right? So topology has its origins from a really long time ago, from graph theory, right? So this is in the 18th century, where Euler he solved this famous problem of the 7 bridges of Königsberg problem. And the problem was this. So you have this town of Königsberg or village, and it had this river passing through it, right? The river is shown in blue. There were 7 bridges that allowed you to cross the river at different points, at different places. The question was, so these bridges were very beautiful, right? So the question was, if a tourist wants to see all the bridges, right? Can you design a tour that takes the tourist through every bridge exactly once and cross all the bridges, right? So there was no clear solution for this. And then Euler came up with what was really the first look at graph theory, right, to solve this problem. And he showed that you cannot do this in this particular case, right? That there is no single tour that will allow you to cross all the bridges while traversing every bridge exactly once. Right? So this is this tour is also named after him, called the Euler tour. Right. So from graph theory, one of the invariants that come to us is this notion of Euler characteristic, right? So this Euler characteristic in the case of graphs is this alternating sum of vertices, edges, and faces. You may have seen this, right? Number of vertices minus the number of edges plus the number of faces, right? So this is called the Euler characteristic of for this graph, and you can compute this for other shapes as well. So this is an invariant. So what does that mean? It means that you take 2 spaces, or to put it very simply, let's start with 2 graphs, right? Which has nodes and arcs. You compute the Euler characteristic for the 2 graphs, right? And if the Euler characteristic are equal, then you say that the 2 spaces are equal in terms of topology up to Euler characteristic, right? So this is a very weak notion of topology. There are stronger notions that were studied. For example, well, connected components is just a part of the Euler characteristic. Then there is this notion of holes that we saw earlier. How many holes are there? How many tunnels are there in different dimensions? So the holes and tunnels were in really 1D. Then you have voids, which are volumes that are enclosed by surfaces. So this is also another type of hole. And you have similar holes in higher dimensions. So these are other invariants that can be used to characterize space. And then you have this notion of homology groups. So these different holes and tunnels can be represented using kind of algebraic structures, particularly these things called homology groups. And they help characterize the topology of a space. And then there are more stronger notions of topology, right? So we are going to restrict ourselves only to these simple ones. So I'll stop with those definitions, right? So that's the notion of topology we're going to use, the study of connectivity of space. So, but we are more interested in computing these topological invariants, right? So computational topology is the study of the algorithms for constructing, storing, representing, measuring, as in the size, and also querying the topology of spaces, right? TDA, or topological data analysis, is really computational topology, but with a focus on doing data analytics, right? So analysis of data, right? So it is a highly interdisciplinary field. You have a lot of interest in TDA from computer scientists. So I come from that background. So where we are interested in designing algorithms, fast computation, we are interested in applications such as visualization and so on. There's a lot of interest in TDA from mathematicians, particularly those who were studying topology, algebraic topology earlier, those who were studying differential topology, or for example, Morse theory, right? And there is a lot of interest now from statisticians, particularly those who are interested in the study of large collections of data and so on. And of course, computer scientists who are studying machine learning or manifold learning and so on. Right? There are tons of applications, as you can imagine. I'm not going to list all of them here. It's just that this is still a young field, TDA, topological data analysis, but it has already been applied to data from various disciplines. Right? Okay. So with that, I want to go a little bit deep and talk about two topological structures, right? But I want to pause just for a minute here in case there are any quick questions about the material that I have shown so far. Right? If there are any questions, please either you can post it or you, yes. So there was one question that was sent to me directly. It's a little bit off topic, so maybe I'll just make sure. So maybe I won't address it right now. This is something to do with quantum and so on. So I won't talk about it now, maybe at the end. Okay, so there is a question that says, what is the meaning of noise? Okay, okay, thanks for raising this question. I'm actually very important. So let me go and show this this picture from before. Right. In order to answer this question, right? So let's say that each of these points, let's say they come from, let's look at very simple example, right? Let's say that I have a Kinect camera, right? I'm assuming that many of you know about the Kinect camera, right? So this is the one that gives you, allows you to take a 3D scan of you, right? And it's used for games and so on. So the Kinect camera, what it does is it gives you geometry. It doesn't give you just a photograph. It gives you, for example, if this is you show the Kinect camera on your face, you will actually get points from your eyes and from your mouth, right? So let's say these are points from your eye and from your mouth, right? But the Kinect camera, let's assume that this is some model that has no nose, right? Please go with me here. But the Kinect camera is not perfect. It is not able to exactly capture the eyes and the mouth. For some reason, it captures and gets you a few points in addition, right? So upfront, I don't know whether these points in the middle are coming from the features in my face, right? Whether it belongs to the mouth or eyes, or it could be the nose, or it is just some due to some error in measurement, right? So these erroneous measurements are what we call noise in the data, right? So the analogy is, if you have a signal, then the signal has some noise, right? If you hear audio, you talk about static noise, right? High frequency noise. So these are undesirable, and we would like to remove them. Okay. We will answer one more question and then I'll move forward. Okay, so please post the question to everybody so that everyone can see. So the question is, can data be infinity points? For sure, yes, but in practice, we don't have such points. We introduce points at infinity only for convenience for some computation, but typically we don't have such points at infinity when you talk about data that comes from real world disciplines. Right? So the question is, can one define metric on the data in the way that noise can be removed? That's a very good question. Right. So there are many ways in which we can handle data, right? So the suggestion here is, can I define a metric on my space, right? Such that it automatically removes the data, right? This is an interesting strategy. I haven't seen it explicitly being employed, except for cases where we talk about comparing structures, and we try to give less weightage to points that are not important. And that is essentially saying that that is essentially defining the metric. So, so I haven't seen it explicitly in this context, but that's a very interesting strategy, right? Okay. So there are two more questions. Let me finish them, and then we'll do the rest later. So does cloud computing and Aadhaar card use TDA extensively? To the best of my knowledge, no. I think they use straightforward machine learning, deduplication, database technologies. TDA is still getting into the mainstream. There are one or two companies that do have solutions, software solutions available out there. They're very popular, but I don't think at least the Aadhaar card, they use TDA. Can TDA be used in face recognition? As far as to, I'm sure it has already been used in computer vision for face recognition. I don't have an explicit reference yet, right? But I'm sure it has been. So I'll kind of pause the questions there, right? And then move forward so that we can cover a little bit more before coming back to the questions. But please post the questions. I'll get them at the end, right? Okay. Right. So I want to next talk about two topological structures. I'm going to give quick definitions. I'm not going to do this in great detail, right? So the first is called the Morse-Smale Complex, right? So the topological structures that I'm going to introduce are primarily going to help us in the study of real valued or scalar functions, right? So we are going to move away from the point cloud or high dimensional data for the rest of this talk, right? So just to reiterate, for the rest of this talk, we are going to focus only on real valued functions or scalar functions. So let's take a real valued function defined on a 2D or a 3D space. So instead of a manifold, just assume this is R2, the Euclidean space, or R3, right? So let's take a function like this. This is a 2D function. And what you're seeing really is the graph of this function, right? So the graph of this function is the surface, and the color tells you what is the value of the function at that particular point, right? So red to yellow. So there are these natural peaks in the data, and then there are these natural valleys in the data, right? So my aim is to understand this scalar function, right? And I want to use topology for this, right? How do I use topology? So I start by talking about gradient lines. So the gradient lines track the steepest descent. So I have annotated the scalar function here with the critical points. So these are where this is where the gradient becomes zero, right? So the local maximum where the gradient is zero, local minimum where again the gradient is zero. You can have also saddles where the gradient is zero. In English, these are also called passes, right, between two mountains, right? So the gradient line here is a white gradient line. This tracks the steepest descent. So another way to think of this is you take a drop of water and place it anywhere on this white curve and let it go. Let's assume that it follows the gradient. So this is the path that it will take towards while it's descending, right? So clearly the gradient along any point on this curve is non-zero, and the limit points are critical points, right, where the gradient is zero, right? So this white curve is called the gradient line, right? So naturally it connects critical points, right? The Morse-Smale complex, also called MS complex, is a partition of my domain, of the entire domain, based on these gradient lines, right? So how do I do the partition? Here is what I do. I look at this gradient line, the steepest descent, and I look at the source and the destination of this gradient line. So the source is naturally this maximum here, and the destination is the minimum here, right? I collect all gradient lines, all such white lines, or I mean, I call them lines, but they are not straight lines, they are curves, right? The term line is meant to represent curves in any dimension here, right? So these gradient lines have a source and origin. I collect all gradient lines that share a common origin and a common destination, right? So for example, all the gradient lines that go from this maximum towards this minimum, they are yellow in color, right? I collect all of them and call that as one cell in my Morse-Smale complex, right? So in this case, the yellow curves, there are an infinite number of them, right? I just show a finite number, but there are an infinite number of these gradient lines. I collect them and I actually get a two-dimensional cell. It is actually a quad, right? It is a quad, a two-dimensional cell. That is one cell of my Morse-Smale complex. So similarly, here is another cell in the Morse-Smale complex, right? So these are two-dimensional cells. Then you have the one-dimensional cells. They fall on the boundary of this two-dimensional cells. So if the source is the maximum and the destination is a saddle, then you have exactly one gradient line that goes between the two. So this happens to be on the boundary of this two-dimensional cell, right? So you have the two-dimensional cells, the one-dimensional cells. The zero-dimensional cells are trivial. They are all the critical points, right? So these cells together partition the entire domain, and that is called the Morse-Smale complex. It is a combinatorial structure. I don't care about the geometry. I just say my nodes are these zero-dimensional cells, and I have arcs connecting the zero-dimensional cells, and then I have the two-dimensional cells, right? So this is called the Morse-Smale complex, right? I hope that is clear. So this is the partition that I get, right? So essentially, I don't care about the function. I now use the combinatorial structure, just this Morse-Smale complex, to study the scalar function. So clearly, it is an abstract representation. I don't care how the function behaves in the interior. I just think of it as one cell. All I know is that there are no critical points in the interior, right? So it turns out that this is a very powerful structure, and it can be used to summarize my scalar function very well, right? So one application that I'm going to talk about next is where you show, you don't show the entire Morse-Smale complex, you only show the maxima, right? All the peaks together with the connecting arcs through these saddles, right? But we do that in 3D, right? So I'm going to show a video here. Let me just play the video.
In this video, we demonstrate our topology-based visual exploration framework for cosmic filaments. Cosmic filaments are gigantic tentacle-like structures comprising of billions of galaxies. They serve as a mass transport mechanism between dense collections of galaxies known as clusters. Regions of space where the density of galaxies is much lower is referred to as cosmic voids. Filaments exist in cluster-like regions and void-like regions. They also connect cluster-like regions across void-like regions. We propose the use of a density range-based query method to interactively explore different kinds of interesting cosmic filaments. The query is efficiently translated to extract relevant filaments from a topological data structure called the hierarchical Morse-Smale Complex. Here, the query was adjusted for filaments within high-density cluster-like regions. The extracted filaments are visualized by the orange linear elements.
Right. So this video, if you could hear
filaments within voids form interesting objects of study.
Let me pause the video. So this was the application that I talked about for cosmology. So the cosmologists, or the people who study the universe, so they are interested in studying these filament regions, right? So what we saw in orange there. And this was very difficult to extract because they appear at different density regimes. So the Morse complex, or the Morse-Smale complex, helps us show them. So what you see, the orange arcs that you saw were essentially the local maxima connected to each other via the saddles, right? Of course, there was a lot more that was done to extract this Morse-Smale complex. So we had to take care of noise and compute the more interesting maxima. So we had to identify the maxima that are not relevant and remove them. So there was a lot of analysis that had to be done here, right? But the end result was that you could produce a useful visualization of the large-scale structure of the universe. So let me play to the rest of the video and then we'll go on.
Are not easily extractable using earlier methods. Here, we extract filaments within void-like regions. The queries demonstrated in this video execute in real time. Thank you for your attention.
So this was work done by one of my PhD students, Nitin, about 4 or 5 years ago, together with cosmologists from Netherlands, who were actually studying this structure and were using just geometric techniques earlier. With the topological technique, they were able to do a much better job of the analysis. Okay, so the next topological structure that I want to define is called the contour tree. Right? So we saw level sets at the beginning of the talk. Let me define them now. Right? So we again start with a scalar function, f. Let's talk about f defined over R2. I think we're going to use an example where d equal to 2 here. Right? And we are going to talk about real valued functions. What we are going to see is level sets. So these are pre-images of a given scalar value, right? So let's take an example. So here is a graph of a scalar function. You can clearly see there is some animation. We'll come to that later. You can see that there are 2 maxima here for this function, 2 minima in blue here, and there are some maxima, also local maxima on the boundary, right? So it's a very simple function. You can think of it as a terrain map, right? What we are interested now is in representing the evolution of the topology of these level sets, right? So what is a pre-image? A pre-image is a set of points that have a given value, right? And I want to study how this pre-image and its topology changes, right? So let's see the video again now. What you see at the boundary of, right, is indeed the level set, right? So this level set, you can see changes topology dramatically, right? Especially when it crosses the critical points. So let's look at one such thing when the level set crosses this green saddle, right? When it crosses the green saddle, you will see that the level set splits into 2 components, right? So exactly there, it's split into 2 components, right? And when it crosses this maximum, this level set component vanishes. And when it crosses this maximum, the second level set component also vanishes, right? So let's look at this again. So when the level set crosses this minimum, you have a new component of the level set. And at this green saddle, the two components merged into one, right? So a lot of topology changes seem to happen at the critical points of this function. So this is a very crucial observation, and actually central to the study of scalar functions using topology, right? So we are able to find a relationship between the topology of the level sets and critical points of the scalar function, right? So this is what we do, and in this entire study. But what is the topological structure? This is computed as follows, right? So uh, um, so like I said, we represent this evolution. So we take every connected component and map it to a point. And the graph that you see overlaid here, right? So where the minima are the nodes, and then you have the saddles, and then you have these arcs. So each of these arcs in this graph represents one connected component of the level set. So here is a good place to see this. You have two connected components of the level set. So that's why you have two arcs corresponding to them, right? So more formally, this is you go from the domain and compute its quotient topology. And the quotient topology is defined by equivalence classes. And the equivalence is given by the connected components of the level sets. So that is only if you are interested in the formal notion, right? So this graph that you get is called the contour tree. It's called a tree because there are no cycles in this case. There are no cycles, as you can see. When your domain is RD, then this graph will have no cycles, right? And it's called the contour tree. It's called the contour tree because each level set component, so in this case, there was this one component that is called a contour, right? So the tree represents the evolution of these contours. This is a very interesting representation because it's able to capture what I mean by what I call topological features, right? So think about, again, in this evolution, think about this component, right? So this component was born at some point of time. In this case, it was actually born at this point, right? When at the minimum. Now this component now becomes 2. So a new component is born, right? So there are 2 components, a new component is born. And the one of the components that was born dies when it crosses this maximum, right? So there are a lot of birth and death events, birth of a component and death of a component. We want to pair them in order to talk about lifetime of these components, right? So we want to talk about how long is a component alive, right? And this pairing gives me something called a topological feature, right? So when we began this sweep, you had a component that was born at this minimum, right? And slowly, as you sweep, there was another component born at this minimum. The 2 components merged at the saddle, right? So instead of talking about them as merge events, I want to talk about them as death events. So the component that was born later died when I crossed the saddle, right? So hence you have a birth-death pair, right? And that I call as a topological feature. So you can represent the size of this feature by computing the lifetime. How long was this feature alive, right? So this is this contour tree, together with this notion of size of features, helps me capture the scalar function in another way, right? So this is a second topological structure that is frequently studied within TDA. Within TDA, there is a notion of topological persistence. You may see this in a future talk. what I'm talking about here is related to topological persistence, but it's not the same. This is just a caveat. Okay, so with that introduction to two topological structures, I'm going to now list some applications. So these are just applications. Again, overview of applications. I won't go into detail here, right? I'll try to finish within 5 minutes. Okay, so the first application is to the study of symmetry, right? So here you have a simple temperature distributed over a conductor, right? So this is a heat conductor, and temperature going from 0 to 1 is what you have here. You can see that the two legs of this conductor are symmetric copies of each other. So their geometry is the same, but the temperature distribution is also the same, right? This is what we want to capture. We want to find such repeating patterns in a scalar field. So when I'm given a scalar function f, I want to find that m1 and m2 are symmetric. And I call them symmetric if there is a transformation T that takes me to M2. In addition, I want the transformation to preserve the scalar function values, right? Finding these symmetric copies is a big challenge because I have to find all such regions. My T is unknown. M sub I could be any subset of M. So this makes it a really challenging problem. And I use topology and topological structures such as the Morse-Smale complex and the contour tree to solve this problem. I won't talk about how I solve this problem. I'll just show you the results. Symmetry is, we see symmetry in every day, right? Right from when we look at the mirror, right? To when we are looking at bridges or natural man-made structures, right? So symmetry is in different forms. For example, in virus exhibits a lot of symmetry. The human adenovirus, for example, exhibits this dodecahedral symmetry, right? With all these tentacles are actually copies of each other. So there is symmetry in molecules, in biomolecules, in proteins. And these symmetries are actually used to find out the structure of these molecules in the first place. There is symmetry even in engineering applications, in flows, and so on, right? Different kinds of symmetry, rotational, translational, reflection, and so on. What we can do when we extract the symmetry is to improve the visualization. So instead of visualizing the data in the form that you see on the top row, if we know the symmetry and we can compute it, right, we can exhibit that symmetry and highlight it, right? So here is the adenovirus visualization where you show explicitly the symmetry, right, as compared to this where the symmetry is not explicitly highlighted. So there can be dodecahedral symmetry. This one shows rotational symmetry. Here you have a very interesting corkscrew symmetry, like the twisting of a screw, right? Here is translational symmetry, right, along the vertical axis. Here is rotational symmetry, but at two levels, one for the blue and one for the red, right? So all these symmetries can be computed and used to highlight with topological structures. So here is just a close-up. So symmetry also, like I said, shows up in the study of fluids. So for example, here is a very simple vortex flow where you can see symmetry at different length scales. This is very tiny length scales to the large length scale. You see symmetric copies of each other. We actually used symmetry to actually find some errors in the simulation in this case. This particular vortex flow should have exhibited only two symmetric copies. We actually found a third. And it turned out that the simulation that we used had an incorrect boundary value. And that was the reason we got a copy on the boundary. So this helped debug that simulation also. Right? That was an interesting artifact. Some of these symmetries are available in the form of a web server. So this is a web server that we have developed, and it's available to study what is called electron microscopy data, and it is used by some of our collaborators, or at least it was used when we developed it. Symmetry over time is essentially periodicity or tracking. So here is flow of some liquid behind a cylinder. So the way you want to see this is you have a fluid flowing from left to right. There is a obstacle at the middle in the form of a cylinder. And what happens to the fluid is it starts becoming turbulent in the wake of this cylinder obstacle, right? And it slowly starts forming vortices, right? And for those of you who have studied fluid dynamics, you may recognize this pattern. This is called the von Karman vortex street. It is a street of vortices, swirling vortices, clockwise and counterclockwise, right? So they form and then eventually dissipate. We are able to use topology to find the periodicity in these vortices. So these vortices get shed at regular periods. So we found the actual period using topological analysis. We found that it was 74 or 75, right? We also found that there was a half period when the vortices switched between clockwise and counterclockwise, right? So this was an interesting application of topology to time-varying fluid studies. We use topology to study and track cyclones. So what you will see in light blue is the cyclone genesis, and you can track this cyclone along the path. You will see that this cyclone is not one of the cyclones that hit us. It hits, for example, Australia, where the cyclones have a different behavior. They are not as powerful as what we see in the tropical regions. These are more difficult to track. They can be extended over large areas, right? So this entire cyan is one cyclone, and we are able to extract that. So lysis is end cyclone. We are able to extract this cyclone even though it is a collection of multiple depressions over a wide area. Final application is again the same flow that we saw earlier, right? But now we are able to, so this is the flow that we saw, right? So this flow is a time-varying data. So what we did was, so this was available over 102 time steps and in 3D, right? So this is the actual data size. We are able to find interesting phases in this data using topological analysis. The way we did that was we compared the first time step with all other time steps to compute a matrix such as this. So each entry in this matrix compares the first time step with, so the first row compares the first time step with all other time steps. The second row compares the second time step with all other time steps, and so on, right? And this is a distance matrix. We study this distance matrix. You can already see interesting patterns. Blue is low values, red is high values. We see a first phase, right? And this phase happens to be when there are no vortices formed. Then you see a second phase, which has a few blue regions, but then there are some red regions. This is where the vortices start forming. There is still no symmetry, right? Or periodicity. Then there is this third block where you see a lot of repeating patterns. So if I zoom in, I actually see that the blue alternates with the red, right? So that is a signature for periodicity. It is periodically becoming the same as the first time step, right? So this is where the periodic vortices are exhibited. And finally, we have the dissipation phase where all the vertices become distorted. And so you have just a red region. So we use topology in this case for summarizing our data, right? This is very important again for time varying data, very difficult to do, especially for long running simulations, right? So I hope that gave you some understanding of the power of topological data analysis. To summarize, there are several challenges when it comes to analyzing feature-rich data and visualizing them. What I introduced to you today was a topology-based representation of features in the data, and to use these features to visualize and explore the data. Right? In our work, we focused on fast algorithms for computing these features. I didn't talk about these results today, but I will encourage you to go look at our lab's webpage, and the software is also available there. We also have some YouTube videos. If you just go to the VGL IISC channel, you should be able to see videos that describe many of these methods. So before ending, I want to definitely acknowledge all the members of our group who did produce all these results. So all the pictures in that I showed in these slides came from research within the lab, except for a few illustrations where I have given explicit acknowledgements. I thank the funding agencies. And I want to end by talking about various opportunities in our group and within IISc. We are always looking for talented students, highly motivated students, postdocs. The openings are posted on my webpage or on the lab's webpage or on the department's webpage. Please take a look. I also want to talk about a startup that came out of the group recently called Mimic. This was actually one of the startups founded by Nitin, who actually worked on the Morse-Smale Complex. So Mimic develops solutions in the medical space. One of their first products is a simulator for endoscopy. So this is to train doctors to do the endoscopy procedure without harming patients. There is a lot of data visualization that goes into a lot of AI, ML, and so on. If you are interested in kind of long-term internships here, especially if you have a good kind of coding background, or you have a background in gaming, or a background in robotics, or electronics, or if you're a mathematician and you're interested in data analytics, please go to Mimic's webpage. They are also looking for longer-term interns. I'm not sure if they're looking for employees as of now, but definitely longer-term interns. Right? So I will stop there. These are some of the links and the YouTube videos that you can look at. Right? And I'm happy now to answer questions. That's the end of my talk. So I do notice again that several of the messages have come to me directly. Not sure if I can post it to all, but let me try to read them. The ones. Okay. So one of the questions is, can we study topological properties like compactness, connectedness, etc. of the data? It's a very good question. Just like you, I also studied topology when I was an undergrad, and my first introduction was to point set topology, right? I think some of this is changing now. There is, to be honest, point set topology has very few applications directly to at least in the TDA context. A lot of what TDA uses is algebraic topology and differential topology, right? So definitely okay, so with that broad kind of answer, the specific answer to this question, I think it comes from Surabhi Tiwari. So the question is, can I study topological properties like connectedness and compactness of data? Connectedness for sure, that's exactly what we are talking about here, right? We have different notions of connectedness and we study them. Compactness is difficult, right? Because when you want to talk about compactness, you want to the kind of assumptions you have to make is rarely satisfied in real world data. Real world data is often a discrete sample, so everything breaks down to just discrete topology, right? So we don't want that. That's too trivial. We often make assumptions about the compactness of the space in order to use the results from topology. But then when we have to apply it, we have to be aware that we are using ideas that were originally proved and introduced for compact spaces. The space that we work with may not be compact. So we have to be careful about this when we use these ideas. Okay. The next question is, the real valued function that I introduced in 2D or 3D manifold, I guess the question is, why do I restrict to 2D and 3D? There is no restriction. I introduced the two structures in 2D and 3D space. They are defined exactly as is in high dimensional space. The contour tree actually can be computed in high dimensional space also. The Morse-Smale complex is not amenable to computation in high dimensional space. It is just, it becomes intractable in 4 and 5 dimensions. Because the complex becomes so big, gradient computations are not reliable anymore, and so on, right? So that's the problem. But the definitions definitely work in higher dimensions. So in fact, there is a restricted version of this that works in higher dimension, and it's used for regression. So regression using topology is also something interesting. So there is a question that says how Okay, so the question is, how can I observe clusters in a kind of a more rigorous form, and how can topology be used to interpret interpret historical data? So the data the domain from which the data comes is irrelevant here. As long as you can map it to high dimensional space, we can use these techniques. So there are different ways to define clusters, right, mathematically. I will encourage you to take up any book on, let's say, data mining to look at clustering techniques. The most common technique is called k-means. And the way they define clusters is by looking at this notion of distortion. How far away is a point from the cluster center? So they use that notion. There are other notions using densities. So there are many ways to define clusters. Pick any book on data mining and it will be able to tell you how to define clusters. The next question is the contour tree finite or infinite? Okay, very good question. The contour tree, the way I described it, is finite. Right. So because the way I think about the contour tree is as a collection of nodes and arcs that connect them. So the arc is a combinatorial object. It's a single arc. It is not a geometric arc, right? It is just a combinatorial arc that connects two endpoints. Now, if you think of this space, the contour tree as a space, right? Then it is an infinite collection of points, right? Because the arc actually is a collection of infinite number of points. But I don't think of it that way. I think of it just as the endpoints and the arc as a single object. Right? Okay. So the question is, can TDA be used for in marine life activity? I don't see why not. There is a lot of applications of TDA to data from different disciplines. So particularly if you are a mathematician, I will encourage you to look at a few lecture material. There are 2 lecture series that are going on now. It's available to everybody. I will just type the acronym here in the chat window, and then please look at it. One is called the Asia Pacific Applied Topology and Geometry Seminar Series, right? So with this search term, you should be able to find it. So this is more recent. And then there is another one called AATRN. This is again Applied Algebraic Topology Research Network. Both have both are seminar series. They are available as videos, YouTube videos that you should be able to download and or just see, or you can even join the mailing list and you will see the lectures live. They talk about several applications. I don't recall seeing something on marine life, but maybe I have missed something. So I encourage you to go and look at this. Several of the speakers actually come from the science disciplines where they actually study their data using TDA. Okay. So the question is, I read that Google Earth used TDA to locate and visualize icebergs in Antarctica. Is it similar to contour trees as in Morse-Smale Complex? And can you give some more insights about its applications here in geography? So unfortunately, I don't know about this result, right? So I cannot give you a specific answer. But if I were to guess, then it most likely the contour tree was used to look at these icebergs, because I'm guessing because Google Earth is essentially talking about the topography. The level sets are more important. So my guess is if TDA was used, then it is contour tree or this notion of persistence diagrams. You may see persistence diagrams in another talk. That was probably used. Right? All right, so there is another question. Are we heading towards, okay, so this was a question from the beginning about quantum computing and topological quantum fields, right? This is completely different from what I have been talking about. Frankly, I don't have any explicit, or I mean, any particular opinion about this, just because I don't know enough to make a to say something. Right, so I'll leave it at that. Is there relations in between contour tree and mapper? Yes, very good question, Priyank Vasu. Yes, the mapper is a similar structure used in TDA, where you look at. So this is a topological structure that captures the shape of a collection of. When you is exactly equal to the contour tree if you move from a collection of points to a continuous set of points. So which is when you have a scalar function, right? So that's the relationship. In fact, it is not the contour tree. I would say Reeb graph. The Reeb graph is the same as contour tree, but it has cycles. So the Reeb graph and the mapper is the discrete version of the Reeb graph. Right? So good question. Okay. Let's see. Right. Okay. There was a question about some of the softwares that are produced from our lab. Please go to the lab's webpage, vgl.csa.isc.ac.in. There should be a link from my webpage also. VGL for Visualization Graphics Lab. You will see a list of software listed there. All these are publicly available. if you are talking about software that we develop, that we use to do our development, we often develop from scratch. Many of the things we develop are in-house. For visualization, we do use a software called ParaView. Okay, so there's a question or a comment, I guess. Are results in TDA approximate only and not exact, right? Good question. Okay, so there are very good results in TDA that show that the results are stable, right? So what that means is that, so maybe before I answer the question, I should say that, so in TDA, we are trying to use topology to analyze data, right? So the data is already available as a sample, right? So I think we have to live with that. So if I am taking a scan of my face, I do not get a full representation of the face. I only get a few points, right? So it's a sample that comes from my face, right? So so the results will be definitely dependent on the sampling density, right? Okay. So given that, TDA, some TDA techniques come with a guarantee that if my input changes a little bit, I think it's perturbed a little bit, the answer that I produce will not change much, right? So this notion of stability is useful. It just says that even if there is some error in your measurements in the sampling, my results will still be the same. They will not change much, right? So the approximation, even if I do an approximation, it says that the approximation is a good approximation, right? Right. So there are, of course, certain results where there is guarantee to get the exact correct answer. So one example is, if I have, let's say I want to compute the number of holes, right? I have a set of points that I showed somewhere in the slide, and I want to exactly compute the number of points. If I know that the sampling density is above certain threshold, I can guarantee using certain techniques that the result will be exact. So there are some results where you get exact results. Okay. I think a last question that I'll probably answer. So you talk about arc. Does this mean there exists path between 0, 1 okay. So the question is, what do I mean by arc, right? So I think the question was in terms of the parameterization. Is it from 0, 1 or -1 to 1? That's not relevant in the context of what I said, right? When I have two critical points, maximum and a saddle, I think of the arc as just something that connects the two. So the arc is just represented by the endpoint. So if A is a maximum and B is a saddle, then AB is my arc. So it is still a combinatorial object. I don't want, in the context of this talk, I don't want to talk about the parameterization. Right? Fine, I guess we are done with all those questions, Professor Vinod. So done there.
Yeah, I think there are no more questions now.
Right.
As expected, the session with Professor Vijay Natarajan has been really inspiring and has opened new channels on our ways of thinking about the subject of topological data analysis. We thank Professor Vijay Natarajan for his valuable time spent with us and giving us an opportunity to take his thought forward. Thank you, sir. Thank you once again.
Thank you.
Thank you, Professor Vijay. Thank you.
Thank you. Good afternoon. Bye.
Thank you.
Our next session will start at 2:15 p.m. Please join before 2 p.m. Thank you.
Thank you.
See you.